Dear organizing committee and respected session chair, thank you for giving me this opportunity to present our paper titled Integrating Deep Feature Extraction with Machine Learning for Robust Lung Cancer Classification on CT Images. I am Mohammad Ibn Shihab Shad will present this presentation. This is the outline of our presentation, which starts with introduction, followed by related work and ends with conclusion and future work. Lung cancer is a major global health challenge. Over 1.79 million deaths and 2.21 million new cases registered every year around the world. Smoking, air pollution, and occupational exposures increase the risk of lung cancer, especially in countries like Bangladesh. Now, AI and deep learning allow us to automatically analyze the lung CT scan images and help to detect cancer earlier. Here are some literature review or related works based on the lung cancer classification using CT scan images. And we can see that many of the deep neural network model has been used for classifying them. While they have achieved a higher accuracy, but they were limited to just binary classification. And while the multi-class classification, the performance dropped has been noticed. And while we were doing this, we observed that overfitting and inconsistent performance is an issue while working with lung CT scan images and the convolutional neural network or deep neural network, while the dataset is limited or annotated data is limited. So our motivation was to move beyond the simple binary classification and include adenocarcinoma, large cell carcinoma, squamous cell carcinoma along with pre-existing benign, malignant and normal cases, and apply explainable AI to visualize regions and generate heat maps on the existing dataset. So this is our dataset description and pre-processing strategy. We can see that the dataset used in this study is very much imbalanced. While the normal has around 30% of image data and while the benign has only 5%. So instead of doing oversampling to balance the dataset or undersampling, we try to move forward with the exact dataset. So for image pre-processing, we have resized the image so that the image can fit into the model. We have performed rotation as a part of image augmentation. We have performed color jitter as image enhancement and normalized that. After that, we have performed feature extraction and it was based on CNN. As we know that CNNs are very much popular and efficient for image classification. While we have a limited amount of image data, that's why in the literature review, the deep neural network model was overfitted and performance was inconsistent. But we can do these deep neural network or CNN model to extract the features. We can see that here the DenseNet 161 has extracted 2208 dimension of data, while the ResNet 18 has extracted only 512 dimension of data. But among them, the EfficientNet B0, which performed better, not in terms of extracting the dimension, it in terms of extracting the dimension and reduce the dimension using PCA and represent the PCA can represent the dimension of EfficientNet B0 better. That's why the EfficientNet B0 was selected. So this was our training strategy. We have pre-processed the image, and we have extracted the features using the principal component analysis PCA. So first of all, we had used the 2D PCA and 3D PCA. After that, we have selected the best feature representation among the 2D and the 3D PCA, and we have used all the CNN model mentioned in the previous slide. After that, we have selected the best feature representation. Then those features were fed to the ML classifiers. After that, we have performed model evaluation and selected the best model based on their performance. So this is the result and discussion section. So we can see that here we have two kind of performance. One is the classification report, and another is the cross validation performance. We can see that while using the 3D PCA, the SVM performed better compared to 2D PCA and all other machine learning model like gradient boosting, random forest. SVM performed better with 3D PCA, and it has around the cross validation accuracy of more than 90%. And here we can see the classification report also, and 3D PCA with SVM perform better. From this slide, cross validation performance, we have noticed that the SVM, the blue one, the SVM performed better in two cases, top 2 and first 3 PCA, and the SVM's performance in each classes was quite better. Here is the graph for that. And this is the confusion matrix. This figure, the left one, shows the confusion matrix with SVM has more stable performance and more higher accuracy and more better performance than the SVM with the 2D feature or the 2D PCA. Here is another thing, that cross validation result. We can see that the cross validation and the validation accuracy of 3D PCA is much more higher with SVM. That's the cross validation accuracy is around 91.5% and validation accuracy around 93% for 3D PCA, whereas the 2D PCA stuck at 87% only. Here is the performance of each fold. The left figure shows the performance with 3D PCA, whereas the right figure shows the performance of each fold with only 2 PCA, first two principal component. So we can see that from here the SVM performs better, it is stable also, and all the model with the 3D PCA perform better compared to the 2D PCA. So after that we have applied the explainable AI. So as we have extracted features from the deep neural network or convolutional neural network model, so we can apply that explainable AI through the convolutional neural network model, and we have find out that these are the heat maps for benign, normal, and there are some other heat maps as well. So the impact of the research was, we can classify the adenocarcinoma, large cell carcinoma, and squamous cell carcinoma as well. The outcome of the research is the 6-class performance around 93% validation accuracy while having 91% cross validation accuracy, and their F1 score aligned with them as well. So we can say that no overfitting or no uh, inconsistent performance noticed here. The limitation was the class imbalancing issue, where what was earlier mentioned, that the benign has less classes, so the benign's performance is relatively weaker than other. So the conclusion is, while the dataset is small, we can do deep neural network as feature extraction and machine learning for classification, and apply GradCam based on the deep neural network and the selected machine learning model. And our future work, that can be multi-level, to generate a multi-level dataset, so that we can find out that both cases can have or not. So here are the references. Thank you for your time and consideration.